There are a couple of things that I forgot to tell you yesterday that needs to be covered before we go into the two dimensional maps. The first thing is, when we were talking about the phenomenon of chaos, we understood that there has to be sensitive dependence on initial condition, and therefore, when we talk about maps, when we talk about the one dimensional maps, then also this phenomenon needs to be understood. And then, while trying to understand what happens in the state space, we realized that there has to be a expanding behavior. When talking about the continuous time dynamical systems, we said that suppose you start with a collection of initial conditions enclosed in a ball, then we have to observe how the whole ball evolves as the time progresses, and then we concluded that if the ball as a whole shrinks, then we do not have, we have only a periodic orbit, or we have a equilibrium point, fixed stable equilibrium point. But in order to have chaos, in order to have sensitive dependence on initial condition, this must expand, stretch. So, we realize that there has to be stretching and folding, because if it goes on stretching, then it will run to infinity. So, another condition was that it has to be bounded, and so there has to be folding. So, stretching and folding, that was the mechanism of generation of chaos. But that we understood in the context of differential equations or flows, and that we need to understand in the context of the maps also. So, how does the stretching and folding happen in, say, the logistic map? That we need to understand in order to actually comprehend how chaos occurs in such a system. For example, in the logistic map given by x n plus 1 is equal to mu x n 1 minus x n. The graph of the map, we had drawn it from 0 to 1. Well, the height of the graph would depend on the value of mu, right? And what value of mu? Okay, the peak position is given by what? Is it is symmetrical. So, mu by 4. You can see that it will be a graph something like this, it will be graph something like this, and so on and so forth, and this peak position is given by so substitute half here, what you get as x n plus 1, that is the position. So, that you get as mu by 4. So, if the range available is 0 to 1, then at what value of mu will the peak reach the value of 1? At 4. That is why we often in this system take the mu range as 0. Okay. Remember the origin of this map, it was invented as a representation of a scaled population of a population, scaled to have the maximum value of 1. So, you need to keep mu confined to these values. So, it will be good for us to go vary between 0 to 1 on the x axis as well as 0 to 1 on the y axis, which means that we are having mu is equal to 4. So, the graph would be something like this. What I will be talking about, that will be applicable to other values of mu also, for which the behavior is chaotic, but for 4 it is definitely chaotic. You can see that here in the computer screen, you can see that here is a chaotic behavior. So, we know it is chaotic. Now, the question is, how is the stretching and folding happening? Take a small amount of some small length along the x n direction, and this length maps to where? Maps to this range, right. So, here is the range where you start, and in here is x n and here is x n plus 1. So, in the next iterate, it expands to this length. So, it stretches, right. If you take two very close initial conditions, the distance between them will increase as it goes there. Okay. So, it stretches, though you might argue that it does not stretch always, because here the slope is less, and therefore, if you take a range here, it will shrink actually, but it is not difficult to see that overall if you take the distance between 0 to half, that maps to the range between 0 to 1. ठीक है ना? So, 0 to half has stretched to 0 to 1. So, you have a stretching. Likewise, so you might say, let us depict it like this. If you have the length 0 to half, in the next iterate that stretches to 0 to 1. So, there is stretching. Okay. Now, if you start from the range 0 to 1 next iterate, where will it go? Again notice that 0 to half will stretch to 0 to 1, and half to 1 will stretch to again back. Okay. So, what is happening is this one will stretch to right 0 to 1, say 0 will map to 0, but half will map to 1. Okay. And 1 will map to 0. So, effectively what has happened is that this line has stretched and again folded, right, and that is why you have sensitive dependence on initial condition. You have this sensitive dependence on initial condition, because if you take this process keeps on repeating, right.
So, when 0 will map to 1 will map to 0,
then
0 will map to
0 will map to 0. No, 0 will map to 0, because 0 is a fixed point. 0 will always map to 0. So, this point always maps to the same point, all right, but the other things go and come back, stretch and get folded, right. Now, notice that we had talked about the Small's horseshoe mapping. Same thing is happening here. In the next iterate, what will happen? This fellow will again be stretched and folded, so that the whole thing remains between 0 and 1. Okay. Boundedness as well as sensitive dependence on initial condition is ensured. Okay. So, that is exactly why you have chaotic orbits in this map. That is how the sensitive dependence on initial condition as well as boundedness is created in this one dimensional map. Clear?
Zero will map to 0, then 0 will be a fixed point.
Yes, 0 is a fixed point, because if you draw a 45-degree line, it passes through 0. So, 0 is a fixed point. If you start exactly from 0, it will always remain on 0, but if you start from a neighborhood of 0, it will not remain there. Okay. Now, you might be interested in knowing what happens beyond 0 to 1. I mean, we have sort of defined things in such a way that things remain bounded to 0 to 1, but at least mathematically there is no reason to think in terms of this only. You might extend, you might say that okay, let my starting point be say minus 0.2 or say 1.2, that is also possible. Just look at what happens, you try to work out logically yourself. You have the 45-degree line here, and you have the graph of the map going like this. So, now you are talking about a starting point that is this side. So, we will need to expand the 45-degree line, and we will need to expand the graph of the map. We will have to extend it. So, we will need to extend it like this. Now, we start from a point that is in the negative side. So, how will we iterate? Again we will not press the calculator, we will do it graphically. So, we will first go to the graph of the map, we will go to the 45-degree line, we will go to the graph of the map, we will go to the 45-degree line, so it will go out to infinity, right. It will go out to infinity. So, any point outside this 0 to 1 range will actually diverge to infinity. Okay. You might ask what happens here. Let us see, if you start from a point that is say outside here, it will map to a point like this. Again you have to go to the 45-degree line, which is, and it will go on, same way it will go out, right. So, anything outside this range will be divergent really, and anything within this range 0 to 1 range will converge. Okay. The other reason is, see, we have taken a range of parameter values 0 to 4. What happens if it is beyond 4? What happens if it goes beyond 4, say 4.1, 4.2? It is not difficult to see that then the height of the map will be larger than 1, right. Here this is your 1, 0 to 1, 0 to 1, and this fellow has gone to a value that is greater than 1. As a result, if you have a chaotic orbit, the chaotic orbit will go on moving, and sometime it will come to this range, that is above the 1 value. Suppose it has come somewhere here. Okay. The next iteration, how will it make the further iterates? For example, suppose it has come here, it will come there, and it will be mapping to somewhere outside. Again it will go and it will go out, which means that if the parameter value is beyond 4, the orbit cannot be stable, it will go out. The details of this will come to a little later, when we understand what this actually means. The other thing that you need to know about this this kind of a structure that you have seen on the computer screen, the period doubling cascade, we have noticed that there are such periodic windows. That means, a period 3 orbit comes into existence here, a period 5 orbit comes into existence here, and so on and so forth. Now, there is a extremely interesting theorem by Sharkovsky, it is called Sharkovsky theorem, it is SAR. I will write the theorem here and then explain what it is. So, you also keep writing. Consider a continuous map function f of x. If for some parameter value f has a periodic orbit of prime period m. What is the meaning of the word prime period? For example, if you have found a period 4 orbit, then it is also a fixed point of the period 2 orbit, it is also a fixed point of the period 1 orbit, but we are not talking about that when you are talking about prime period. Prime period means where this is the largest number in the periodicity. So, period m, then
period 3, if we get a period 3 orbit, then the name is 3.
Yes, yes. If you get a period 3 orbit, then you might say that it is the orbit orbit that comes back 3 iterations later. So, it is its m is 3, okay, that way. F also has for the same parameter value a periodic orbit n where n occurs to the right of m in the following ordered set. Now, this set is important. It follows from number theory 3 to 5 to 7 2 goes to infinity. Now, 2 times 3 to 2 times 5 to 2 times 7 goes to infinity, to 2 square times 3 to 2 square times 5, and this one continues. See what happens, we have it follows from number theory, we are making ordered sets, the numbers. See, the first set is 3, 5, 7, 9, 11, so on and so forth, goes up to infinity. Then comes 2 times 3, 2 times 5, 2 times 7, and that also goes to infinity.
3579 or 3579?
3579, let it be, because I am not talking about the primes and all, just the order set. Then it goes to 2 square times 3, 2 square times 5, and so on and so forth. Then it goes to 2 cube times 3, and so on and so forth. If it goes this way, then after some time you will realize that you have covered the whole number set except the multiples of 2. So, then it continues and you have to say 8, 4, 2, 1. So, this is a whole set that covers the whole number theory, whole number set, natural numbers. No, it is actually here, it continues in the right hand side. So, this continues to this. So, just consider this number set, it is arranged in a particular order. First it goes up as 3, 5, 7, 9, 11, and so on and so forth, goes to infinity. Then it goes to 2 times 3, 2 times 5, 2 times 7, and goes to infinity. 4 times 3, 4 times 5 goes to infinity. And at the end of the day, you have left these numbers, the set containing the multiples of 2, and then it goes into the descending order, ultimately arriving at 1.
So, when it arrives at 1?
It finally arrives at 1. The last number in this ordered set is 1. The last number in this ordered set is 1. The first number in this ordered set is 3. Okay. Now, notice what this theorem says. The theorem says, now look at the bifurcation diagram, it will be easier to understand here. Say at a particular point here, say, can you see this cursor? If a periodic orbit of order n, prime order, prime period m occurs here, then suppose m is somewhere here, then all that to the left of it, sorry, to the right of it will also occur. So, let us see, if you ever find anywhere period 7, then all the orbits to the right of it must also occur there. Okay. So, if you ever find period 5, all the orbits to the right of it must also occur there. You might ask, where are they? They are all unstable periodic orbits, because as it was going from the period 1 to period 2 and so on and so forth, you found that they all became unstable, but they continue to exist. So, all these orbits will be occurring. If you ever find a period 1 orbit, what does it mean? No, nothing is occurring, no other thing is occurring. See, that is here. That immediately brings to the conclusion that here there is no other periodic orbit in this part. Period 2, yeah, 1 is also there. Period 2, the one fellow is also there, right? Period 1 is also there. Now go to period 4, 1 and 2 are also there. So, as you go this way, you will find that if you ever find, when you ultimately arrive at this period 3 window, when you ultimately arrive at this period 3 window here, yes, periodic orbits of all periodic series must occur by this theorem. All natural numbers are covered.
Then if you are covering everything, then why this prime period? Why this word prime period?
Because if you are talking about say period 8, then that is also a fixed point of period 4. So, those things need to be eliminated. When I say period 8, I am saying period 8 only. There should not be any
the maximum period.
Yeah, there should not be any complication as far as the definition is concerned. See, period 1, this point, see, let me draw. What happened? Yeah, this one is also the fixed point of the period 8 behavior. So, when I am talking about period 8 behavior, I am not talking about this one, though that is also a fixed point of the period 8 map. That is the point of the prime period, because those which are also the fixed point of any lower periodicity, they are eliminated, then only you get the.
So, these primes have nothing to do with the
prime number. No, it has nothing to do with the prime numbers. Yes.
But we said last one like 8, 4, 2, 1 is there. That means before it 16 will be there.
Yes, before that 16 will be there.
Will be there.
Yeah, that comes from infinity again.
So infinity is also.
Yeah. So, that is a descending order. Here also it starts from infinity, but in all these intervals you find things accumulate into infinity. So, if you ever find a periodic orbit with period 3, which means that all the periodic series must be there. Okay. All the periodic series must be there, but all these periodic series are unstable. So, if you have a period 3 orbit, which means that at the same time for the same parameter value, all the other periodic series are existing, and that is why the famous theorem by Lee and York, period 3 implies chaos, that can be said to be a corollary of this Sharkovsky theorem, but the historical fact is that York and other people, they discovered it independently without any idea that Sharkovsky actually had this theorem already in place, but Sharkovsky preceded those people. In fact, much of the developments in fields related to mathematics, you will find happened in the erstwhile Soviet Union, while people did not know that these things already had been done. This is one of such theorems. Clear? So, if in any system, this means if in any system, if you ever find a period 5 orbit, then except for period 3, all the other orbits must be existing there. If you ever find period 3, all number periodicities, including period infinity, must be existing, means there should be chaotic orbit.
Does it, I mean, there was in the window there was this global phenomena that you didn't explain that thing. This is the reason behind this.
His question is in this window.
Period 3 windows.
In the period 3 window, the chaotic orbit is there. All these periodicities are there existing. Only thing is that they are all unstable, while the period 3 orbit has become stable. That is why you see all the initial conditions converging onto the period 3 orbit.
So I was trying to say that even the period 3 orbit, that was also actually giving rise to chaos. And that in the window.
Oh no. I'll come to that. Yes, if you expand it. No, I have to draw it afresh. Yes, you are talking about this window. This, yes, it is related to that. It is related to that, but this phenomenon I will explain a little later. This only tells you that this orbit was actually pre-existing. It was actually pre-existing, and it became a part of the orbit, part of the chaotic orbit at this particular point of value, but this orbit was actually pre-existing. One clue I can possibly give you, notice that at this period 3 point, there was a saddle and a node. This is the node, this is the stable fixed point, this is the unstable fixed point saddle, and that fellow where it intersects with the chaotic orbit, that is exactly where you find this sudden expansion. Okay, we will work on that line later when we talk in details about this particular phenomenon. Let us come to what we actually plan to discuss today, that is 2D maps. So, we ended the last class yesterday with saying that let us consider x n plus 1 is equal to f 1 of x n y n, and y n plus 1 is equal to another function so that will be a 2D map. Likewise, there can be 3D maps, 4D maps, all possibilities, but let us take the next step to the 2D maps. So, you have the x and y now, x and y, and then what is this fellow doing, this map doing? You should start from a point which means it has a particular value of x and y, x n y n. By this it takes a jump to another point. Okay. And if you go on applying this map again and again, that means if from starting from here you get the first one, apply the same map on this one, you get another point, apply the same map on this one, you get another point, and so on and so forth, you get a succession of points. In other words, you are iterating the map. Remember, this pronunciation is not iterate, its pronunciation is iterate. Many Indians make this mistake of wrongly pronouncing it. So, you are iterating the map, like the pronunciation of Linux is Linux, not Linux. Many people make this mistake of pronouncing it wrongly. So, here you are iterating it, and as a result you will get a sequence of points. A sequence of points, if they converge like so onto a point, then we would say the orbit is stable, right. So, here is x n plus 1, x n plus 2, x n plus 3, and so on and so forth, but ultimately if you observe them to be convergent sequence, then you have a stable behavior. Can you picturize what is happening in the actual continuous time state space, in which you have placed a Poincare section, and on the Poincare section you are seeing this, a sequence of points that is convergent. What is actually happening in the 3D continuous time space? It is actually converging onto a limit cycle, starting from an initial condition that is away from the limit cycle. So, if you cut it, it will intersect at points that are progressively closer to the ultimately the point at which the limit cycle crosses the Poincare plane. So, you are actually then by this method you are trying to understand the stability of the limit cycle, but you are doing it with a much simpler tool, namely a map of this form. Okay.
I mean, limit cycle can exist for a two-dimensional system also.
No, limit cycle can exist for a three-dimensional system. Okay, limit cycle can exist for a 2D system, yes, but period 2 orbit can exist only for a 3D system. Yes. That is why when we talk about the two-dimensional map, you might imagine that we are considering a three-dimensional continuous time system in which you have placed a Poincare plane which is 2D. Okay.
That is for one dimension there is no like Poincare section is meaningless.
Not really meaningless, because as he said, there can be a limit cycle in 2D like this, and you can place a Poincare plane. In that case, it will be a line. Okay. So, suppose this is your so his question is, can you have is one dimensional map meaningful in the sense of the Poincare section? Yes, it is meaningful in the sense of the following. Supposing there is a 2D space in which you have got a periodic orbit. So, here if you want to place a Poincare section, it will no longer be a plane, it will be just a section. And if you start from an initial condition somewhere here, you will see it coming here and then again coming here. So, here you see a sequence of points, ultimately it will converge onto this point, right, and that is exactly what we were studying as the map. So, here is the map, 1D map. But there is another part of the story. Here, if the system is autonomous, then you cannot have a periodic orbit of periodicity greater than 1 if it is autonomous system. I explained that earlier. If it is autonomous system, you cannot have an orbit like this in 2D, because then this would be an intersection point. You cannot have an intersection in a orbit.
So that is for all the systems.
No, it is this argument will work only for autonomous systems. For non-autonomous systems, where you have got a periodic forcing function, that in that case time becomes a third variable, so that you can have this kind of orbits, you can have this type of orbits with 2D, 2 spatial dimensions and 1 time dimension. Okay.
So then, I mean, oscillator you will say it's autonomous or non-autonomous?
Depending on
Noise is an input.
no, noise input is not considered to be an input, because you are ultimately studying the oscillatory behavior. Noise is something spurious, that is not predicted. Here we are talking about everything that is modelable, that you can write a differential equation for. You cannot write a differential equation for noise. So, here we are in an oscillator, we are talking about any system, if there is some kind of a periodic input from outside, then it is non-autonomous. If it is an oscillator that oscillates by itself without any periodic forcing, then it is an autonomous system. Naturally, it brings you to the conclusion that you cannot have a oscillator without 3 dimensions. So, you can still have a periodic orbit or a chaotic orbit or everything in 2D if the system is periodically forced, non-autonomous. In that case, if you place the Poincare section, it will still be 1D. So, in that sense, 1D maps are still relevant as a Poincare plane.
So, but LC oscillator is 2D.
What?
LC oscillator.
Just if you have LC, then it is not it cannot generate a orbit like this.
But
It only generates orbit like this.
it's also an oscillator.
Yes, this is an oscillator. You can have this. An LC oscillator cannot have an orbit like this. It will have always an orbit like this, and it is mathematically showable that you cannot have an oscillation like this,
So when you have interest,
an oscillation like this simply by LC. You cannot have.
even if there is an intersection the time dimension is you are neglecting, because there is, I mean, if you take the time dimension also, there can be no intersection because two times will be same.
No, if you are considering the autonomous system, their time is evolving like this, right. As you are going around the orbit, time is going forward.
So the time dimension is not shown there, isn't it?
No, in that case, what will you say as a periodic orbit? A periodic orbit means which comes back to the same value of the state after some time, that is a periodic orbit. Now, you notice that here, if you start from here, after this much it has come back to the same state, okay. And therefore, it is in every sense the same point. But if there is a periodic forcing, say a sinusoidal a sin omega t kind of term, then it might come back to the same point, but it may be a different phase of the forcing. So, it will be a different point effectively. Where were we? We are talking about this. So, you have this sequence of points ultimately converging, and like in the 2D systems, or like in the continuous time systems, when we had a equilibrium point, how did we study the behavior of that? By locally linearizing. Here also we will locally linearize around this point and try to study its behavior. And local linearization again will be done in the same way by taking the Jacobian matrix. So, if you have the F1 and F2 given, then your Jacobian matrix will be given by right. Fine. Now, what are the possibilities out of this? As we have already seen in case of continuous time system, 2D continuous time systems, this having obtained the Jacobian, this essentially tells that if this is my fixed point, here I am considering only in the local linear root. So, I am taking a magnifying glass and only looking at the closed neighborhood of it, and the behavior around it will be given by its eigenvalues. That is what we have concluded. I am not repeating that. We have already concluded by some logical procedure that the behavior around it will be given by the eigenvalues. Here also it is so. And we have also seen what can be the different types of eigenvalues. It can be real, it can be positive, it can be negative, it can be complex. So, these are the possibilities. Fine. So, let us see what happens initially. Let us see what happens if the eigenvalues are positive, real. If the eigenvalues are positive and real, then there should be identifiable, drawable eigenvectors. Okay. You can draw the eigenvectors. Imagine that here is a fixed point and here are the two eigenvectors. Now, suppose I start from this point, here is a fixed point and here is my starting initial condition. My question is, where will it go? Obviously, if this is the eigenvector, then where will it land next will be given by this vector times the eigenvalue. Okay. So, if the eigenvalue is less than 1, then this distance will be multiplied by a number less than 1. As a result, it will land somewhere closer. So, this will be the map. Okay. Notice one important distinction between what we learnt in the case of the differential equation and what we are learning here. In case of the differential equation, our situation was x dot y dot is equal to this Jacobian matrix times x y. Here our situation is that x n plus 1 y n plus 1 is equal to that Jacobian matrix times x n y n. So, in case of the differential equation, this right hand side tells the direction of its motion and how fast it will move. Okay. And you really have to solve the differential equation in order to see where it goes, but here it directly tells you where it will land next. It directly tells where it will land next, and that has an important bearing on our conclusions about the matrix A and the eigenvalues. For example, as you have seen that if the eigenvalue is less than 1 positive, then it will go like this. Where will the next iterate be? Again this distance will be multiplied by that same number. So, it will come, it will not move by the same extent, same length will be multiplied by the same factor. So, it will be closer, but not this distance will not be same, and it is not difficult to see that in progressive iterates it will progressively converge onto the fixed point. Clear? If the eigenvalue happens to be greater than 1, say along this direction it is greater than 1. So, where will it go next? This number, this distance will be multiplied by a number that is greater than 1. So, it will map like this, and it will never converge onto the fixed point. Do you see that we are now arriving at a condition for stability? System will be stable if the eigenvalues are less than 1, which is a different condition from what we learned for the continuous time system. There the condition was that it has to be, real part has to be in the negative side, but here the condition is different, condition for stability is different. Okay. Now, let us understand what will happen if you have negative eigenvalues. Suppose this is the fixed point and these are the two. Suppose you start from here with this is a direction, eigen direction with a negative eigenvalue. So, this distance will be multiplied by a negative number, which means that it will come somewhere here. So, it will flip.
So, will it be multiplied by negative number or e to the power?
No, e to the power things come in case of the continuous time systems. Here see the behavior is like this, x n plus 1 is equal to that times the vector itself, right. Wait, let me answer the question properly. When you do the diagonalization of this,
Over there is a dx dt term, so that's
here there was a dx dt and that led to the e to the power term. Here there is no need, that is why the maps are far simpler than differential equations.
so basically the 2 by 2 matrix in differential equation we used to get for a 2D system.
Yes.
But here the 2 by 2 are getting for a 3D system.
Once we have got this, got the actual functional form or some kind of a representation like this.
It is actually greater than 2D.
No, its corresponding continuous time representation has to be greater than 2D, all right, greater than or equal to 2D, because in case of non-autonomous system it will be the same dimension. But once we have got this one, we will forget about the continuous time system. Only in our understanding we will relate, but we will not do the mathematics with the continuous time description any further, because that is far more complicated. Once we have got this, we have got a far more handleable description. Okay. So, in this case what is happening? It is flipping to the other side if the eigenvalue is negative. It is flipping to the other side. Next iterate, it will again flip to this. Next iterate, it will again flip to this side, so on and so forth. But ultimately it will converge. But it will converge while flipping between the sides. That is why such a behavior is called a flip behavior. Flip. Okay. Now, we are in a position to sort of name equilibrium. If a fixed point has, notice that I am using two different words. In continuous time dynamical systems, we were using the word equilibrium point, while in a discrete time dynamical system or a map, we are using the word fixed point. So, these are the nomenclatures, though in some books you will find that they are interchangeably being used. I do not prefer that in order to distinguish between the two types of systems. So, we will talk about fixed points here. So, first condition, the eigenvalues, both eigenvalues between 0 and 1, positive and between 0 and 1. Then if you have the fixed point here and if you have the two eigen directions like this, then what will be the behavior? In this direction it will be, in this direction also it will be like this. Okay. Okay. So, the fixed point becomes an attracting fixed point. This will be called a regular attractor. This will be called a regular attractor. Now, suppose you have taken a situation where you have one eigenvalue between 0 and the other eigenvalue between then what will be the behavior? You will draw the positions like this, and so there will be one direction along which it will be positive, another direction. So, let us say this direction along which it is positive. So, it will behave like this, but along this direction it will be okay. So, it is a flip direction, it will be called a flip attractor. All right. If you have a situation where and then it will no longer remain an attractor. Okay. It will, its behavior will become like so. Along the direction of lambda 1, there will be another direction of lambda 2. Along the direction of lambda 1, it will be so on and so forth, it will be converging. But along the direction lambda 2, eigen direction associated with lambda 2, it will be go out. If you start from an initial condition other than the on the eigenvectors, what will happen? Say if you start from here, what will its behavior be? As time progresses, along this direction it will shrink, it will come closer to this, along that direction it will expand and it will go out. So, you will get a succession point something like this. So, it will go out. Notice that it is coming closer along in the okay. Imagine it like this, that it has a component along this eigen direction as well as along this eigen direction. The component along this eigen direction will decrease and component along this eigen direction will increase, and so it will be 1, 2, 3, 4, 5 and so on, so it will go out. One thing that I find often students take time to digest is that the movement will not be a continuous movement, it will be discrete jumps. The movements will be discrete jumps. Such a fixed point will be called a regular saddle, because it also has the property of a saddle. I told you, no, the saddle has a behavior something like this. So, its direction in which it is stable is this direction, and the direction in which it is unstable is sort of this direction. So, this is also a saddle behavior. We have come across the saddle behavior in continuous time systems, similar behavior here. If you have and lambda 2 less than minus 1, then you will have the fixed point and the eigendirections, sorry, which has not been very well drawn here. Then suppose this is the lambda 1 direction and this is the lambda 2 direction. What will be the behavior in lambda 1 direction? Same, so on and so forth. What will be the behavior in the lambda 2 direction? Flip, but at the same time going out. So, if you start from a point close, it will go like this. The lines that I am drawing are not really lines, I am drawing discrete jumps, but in order to show the discrete jumps I am drawing. Do not imagine that it will actually continuously move this way, it will take discrete jumps along this eigen direction. Can you tell me what will the behavior be if the starting point is away from the eigen directions? Say my starting point is somewhere here. All right, it will come closer to this one. No, there is nothing ellipse here, because it discretely jumps, and naturally it cannot go into elliptical path, which is a continuous time idea ported here, that will not work. Notice that in the next jump the distance along this will reduce, distance along that will increase, but at this time it has to flip from this side to that. So, the next iteration will be somewhere here, third iteration will be somewhere here, fourth iteration will get there, fifth iteration there. Okay. So, 1, 2, 3, 4, 5, 6, 7, so on and so forth, it will go out. Ultimately, it is coming closer, but it is flipping from one side to the other. Such a fixed point will be called a flip saddle. It is a saddle of course, but it has a property, flipping property from one side to the other. So, it will be called a flip saddle. Ultimately, it will go out into infinity, but while it is flipping from one side to the other, and it will go out along this eigen direction. It will converge progressively along this eigen direction, and it will go out along that eigen direction. And since we are considering it to be a linear system, we might say that it will go to infinity, but actually since it is a nonlinear system, it might not go to infinity. We will come to those issues later, but as far as the linear description is concerned, it is convenient for us to understand that it will tend to infinity, but along these eigen directions. Okay. Fine. So, we will continue with this in the next class.